thermochemistry. It's the study of changes in heat. Energy of a system plus the energy of the surroundings is equal to the energy of the universe. We can't figure out how much energy something has, but we can figure out the change of energy that's transferred. So the change of energy of the system plus the change of energy of the surroundings is equal to the change of the energy of the universe. Let's derive this further until we get down here. The change of energy of the system is equal to the negative change of the energy of the surroundings, which means whatever energy is being given off from here can go into the system. And it can be done as vice versa as well. You just have to change this into a negative and turn this into a positive. So energy can't be created or destroyed. It is conserved between these two variables, system and surroundings. So if they're conserved, they just go back and forth in opposition. Well, what is this heat quantity, the Q? Well, Q is energy. So how do we figure out the total heat quantity of something, how much energy it has? Well, like I said up here, it's only going to be looked at the energy change, the change of the energy. Well, delta H is going to be represented as that. So if this is equal to this, let's look at first what Q is further. Q is equal to the internal energy of something and the work done by that something. Well, this is heat quantity, and this is the work done. What the heck does internal energy mean? Let's break this down further and isolate it so that Q minus W. We can't figure out what Q minus W is because if that gives us our internal energy, it's too difficult to find out. That's a total amount of potential energy, a total amount of kinetic energy of all the particles, all summed up, zillion particles. It's too difficult. We can't figure it out. It's not quantifiable. It's honestly useless to us. So we have to use the change, which is known here as the delta. The delta here is important to us because we can figure out how much energy is being transferred. So if this is the case, this is our delta. That's a good sign. We want the change. We don't really want an absolute value like this. So let's now focus on the heat and the work over here. These are the ways we should be looking at energy, solely based on the transfer between systems. But right now, it's not. Only this one is a delta. These have to be delta as well. Well, heat and work are path functions, so it matters about the final and the initial, the path that it takes in between. But if we change work into a state function, so it's not looking at the path it takes, it's only looking at the difference between the final and the initial state, we can actually change work into pressure as constant and the change in volume. Look at my 20-minute video if you want to look further into this. So if this becomes a state function, and this was also a state function in the beginning, if we rearrange this for Q, Q equals this sum of state functions. So technically Q becomes a state function. So Q is equal to the change of energy.